Today we are walking through the paper titled Orca the World is in Your Mind.
What is Orca trying to solve?
The paper argues that next tick tone, next frame, and next action prediction are each too narrow on their own. Orca instead tries to learn a shared latent state of the world, then read that state out as language, images, or actions.
So the target is not just better captions or prettier images, right?
Right. The target is whether the model has learned a reusable world state. The authors freeze Orca's backbone after pre-training. Train only lightweight readout modules, and then ask whether that frozen latent supports understanding, visual prediction, and robot action.
What was missing in the earlier families of models?
Language models mostly predict the next token. Image and video generators mostly predict visual continuation. And action models predict robot actions. Orca's criticism is that those objectives bind the model to one output form, while world change itself should be the thing being modeled. Here is the overall framework. Multimodal world signals enter an encoder called Orca. The encoder learns a world latent representation, and separate decoders read it out to text, images, actions, and other possible modalities.
The diagram splits learning into two paths.
Unconscious learning means observation-only transition learning from continuous video. It teaches dense natural changes such as motion, occlusion, and object interaction. Conscious learning adds language conditions, events, questions, and answers. So the model also learns sparse meaningful changes tied to instructions or causal descriptions.
Where does the QA fit into that encoder?
VQA is the language-facing part of conscious learning. The model sees video plus a question and learns to produce an answer. That keeps the latent connected to semantic and common sense information instead of making it only a visual transition code. The data diagram shows how those objectives are supported. Video covers egocentric interaction, exocentric manipulation, robot execution without action labels, and natural dynamics. Event data adds coarse and fine captions. VQA data adds question-answer supervision.
How large is that inventory?
The authors report 125,000 hours of general video data, 160 million event annotations, and 11.5 million general VQA examples. In this version, they train on 1/10 of the video inventory, which matters later because they still see scaling trends. The formal target is next state prediction. This expression says that a future or past state is sampled from a model conditioned on the current state, hidden dynamics, and explicit conditions.
Why include both hidden dynamics and explicit conditions?
Because some change happens naturally, like objects moving or scenes evolving, while other change is driven by an instruction or event. The equation lets Orca model both what the world tends to do and what a condition asks it to do. The training loss combines the three objectives: observation transition, event condition transition, and VQA response generation are weighted together so the same latent is constrained by dynamics, language conditions, and semantic answers.
So the loss is not only about language accuracy.
Exactly. 2 parts supervise predicted visual latent tests, and 1 part supervises language answers. That is why the later ablation is important. Using all three objectives gives the most balanced threadouts across text, image, and action. Now to the first result. This plot asks whether the learning paradigm scales as pre-training hours increase. The 4 billion parameter model also stays below the 0.8 billion parameter model.
What should he take from the lower purple curve?
It means the larger Orca learns the combined objective better, and neither curve has flattened out. The authors use that as evidence that next state prediction is still benefiting from more data and more capacity. The next result is the key downstream probe. With the backbone frozen, text generation, image prediction, and action generation all improve as pre-training grows. The 4 billion parameter version is consistently stronger than the smaller one.
The action curve improves, even though the pre-training did not use action labels.
Yes, that is one of the paper's stronger claims. Video-only state transition learning appears to create information that can later help real robot action readout, even when the action decoder is trained separately afterward. For text generation, Orca is compared with world model baselines and vision language baselines. Orca 4 billion reaches an average of 51.8, compared with 46.7 for Q and 3.5 for billion and around 30 for EMU-style world models in this table.
Does the paper break down what kind of text reasoning improved?
It groups benchmark samples into 4 capability dimensions. Against Q and 3.5 for billion. Orca 4 billion is higher by 12.27 percentage points on state transition, 5.19 on common sense reasoning, 0.57 on spatial relations, and 8.52 on dynamic motion. For image prediction, the task is not ordinary image generation. PRICEV 0.1 asks whether a model can predict the next real-world interaction state under constraints. Orca 4 billion plus its a billion image decoder gets an average of 59.8, ahead of Flux 2 at 56.1 and Omnigen 2 at 39.6.
In these examples, what is Orca preserving data?
The paper says the baselines often add irrelevant objects, teleport objects, create hallucinated hands, or miss the instruction. Orca better preserves the robot body, the scene, the object contact, and the requested interaction outcome. For action generation, the real robot setup uses out-of-distribution environments and objects. Overall, Orca reaches a rule-based score of 32.4, while VJEPA 2.1 gets 17 points, Auto and Q 3.5 gets 10.5 with the same from scratch action expert setup.
Is the action result only about final success?
No, the diagnostics also track intermediate progress and recovery. Orca has the highest overall drawdown recovery ratio at 30.3, meaning it is better at continuing after progress drops. The paper describes it as moving further, getting stuck less often, and recovering more effectively after mistakes.
What limitations should viewers keep in mind?
The authors are direct that Orca is early. It mainly learns from vision and language, not audio, touch, force, light, or participation. Its visual state prediction is supervised through a frozen vision encoder space, and the experiments are only at 0.8 billion and 4 billion scale. They also note that PRICE 0.1 is still limited in scale and diversity. Transition supervision is mostly short horizon, and the downstream readouts cover only language, vision, and action, so the paper is best read as an exploratory milestone, not a complete world foundation model.
So what is the final takeaway?
The main takeaway is that Orca shifts the center of modeling from a single output modality to world state transition. Its frozen latent improves text, image, and action readouts as pre-training scales, and the results suggest that a shared world latent can carry useful structure across very different tasks.
That makes the contribution much clearer. It is a test of whether a learned world state can be reused, not just another task-specific model.
Exactly. That wraps up this paper walkthrough.